Hello everyone, my name is Adhwa Nabila S T from Class MB-48-01. Today I will explain about optimization and differentiation in economic and business mathematics. We will discuss how to find maximum and minimum point for function with one variable, extreme point for function with two variables, partial derivative, second partial derivative, and total partial derivative. I will also give example and solve each problem step by step. First, optimization function with one variable. Let us begin with optimization for a function with one variable. The goal to find the maximum or minimum value of a function. We do this by finding the stationary point using the first and second derivative. First, to find the stationary point, we set the first derivative equal to 0. For example, y equals x cubed minus 12x squared plus 36x plus 8. The first derivative of y with respect to x is 3x squared minus 24x plus 36. We set the first derivative equal to 0. 3x squared minus 24x plus 36 equals 0. Divide both sides by 3. X squared minus x plus 12 equals 0. Factor the equation. Open parenthesis, x minus 6 close parenthesis times open parenthesis, x minus 2 close parenthesis equals 0. So, x equals 6 or equals 2. Next, we ask the second derivative to determine the type of stationary point. The second derivative of y with respect to x is 6x minus 24. Substitute x equals 2. 6 times 2 minus 24 equals 12. Minus 24 equals negative 12. Because the result is less than 0, this point is a maximum. Substitute x equals 6. 6 times 6 minus 24 equals 36 minus 24 equals 12. Because the result is greater than 0, this point is a minimum. Now let us talk about extreme point. Extreme point are where a function reaches a local maximum or minimum. For a function of two variables, we find the critical point by setting both partial derivative to 0 and use the second derivative test with the discriminant. For example, f of x and y equals x squared minus 2x plus y squared. The partial derivative of f with respect to x is 2x minus 2. The partial of f with respect to y is 2y. Set both the to 0, 2x minus 2 equals 0, so x equals 1, 2y equals 0, 2y equals 0. So the critical point is open parenthesis 1, 0 close parenthesis. Now, find the second partial derivative. The second partial derivative with the respect is x is 2. The second partial derivative with the respect to y is 2. The mixed partial derivative is 0. Calculate the discriminant. D equals 2 times 2 minus 0 squared equals 4. Because D is greater that 0 and second partial derivative with respect to x is greater than 0, the point open parenthesis 1, 0 close parenthesis is a minimum. Now, let us continue with partial derivative. Suppose y equals x squared plus 2xy plus x cubed z. The partial derivative of y with respect to x is 2x plus 2y plus 3x squared z. The partial of y with respect to z is x cubed. Next, second partial are the derivative of the first partial derivative. Suppose z equals x cubed minus 9xy minus 3y squared. The partial derivative of z with respect to x is 3x squared minus 9y. The second partial derivative with respect to x twice is 6x. The mix second partial derivative with respect to x and y is negative 9. Next, let's discuss total partial differentiation. If z equals 5x squared minus 12xy plus 6y to power of 4. The total differential dz is open parenthesis 10x minus 12 close parenthesis times dx plus open parenthesis negative 12 x plus 24 y cubed close parenthesis times 2y. Today, we have discussed optimization for function with one variable, extreme point, partial derivative, second partial derivative, dan total partial differentiation. Each concept built on the previous one, and together they help us analyze and solve problem involving function of one or more variable. Thank you for attention. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Alif Aulia Rizki. I'm student from class MB-48-01. Today, we're going to learn about elasticity in economics, specifically Prince elasticity of demand and price elasticity of supply. This concept help us understand how sensitive the quantity demand of supply of the product is to change in its price. Now I want to explain the formula for price elasticity of demand. A sub D equals the percentage change in quantity divided by the percentage change in price, with equals quantity to minus quantity equals quantity to minus quantity 1 over quantity divided by price to minus price 1 over price, with equals the limit as delta P a process 0 of delta Q over Q divided by delta P over P, with equals the derivative of quantity demanded with respect to price multiplied by price over quantity demand. So next, elasticity classification. Value of a type of elasticity greater than 1 elastic, less than 1 inelastic, equal to unitary elastic, equal to 0, perfectly inelastic, equal to infinity, perfectly elastic. And next, the price elasticity of supply, how much quantity supply change in response to change in price. A sub S equals the Q sub S over dP times P over Q sub S. Example, given supply, function QS equals minus 200 plus 7P2. Find the elasticity of supply at P equals 10, P equals 50, 15. Step 1. dq sub S over d P equals the derivative of negative 200 plus 7P squared, which is 14P. Step 2. At P equals 10, Q sub S equals negative 200 plus 7 times 10 squared, which is 500 dq sub S over dP equals 14 times 10, which is 140. Elastic supply at P equals 10. At P equals 15, Q sub S equals negative 200 plus 7 times 15 squared, which is 1375. dq sub S over dP equals 14 times 15, which is 210. A sub equals 210 times 15 over 2375, which is approximately 2.29. Still elastic at P equals 15. Conclusion. Key takeaways. Elastic help us understand how much customer of producer respond of price change. Demand elastic is usually negative due to the inverse price demand relationship. Supply elastic is usually positive and depends on how easily producer can adjust output. In our example, the supply was elastic at both P equals 10 and P equals 15. Thank you. Maybe just this. from me. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Elviana Salma H K. I'm from MB-48-01. Today, I'm going to explain the topic of two-variable optimization, both with and without constraint, using the Lagrange method. This method is used to maximize or minimize a function subject to a constraint. First, I'm going to explain the with constraint. First, we define the Lagrangian function, written as L of xy lambda equals f of xy plus lambda times open bracket minus c minus g of xy close bracket. Step 2, take the first order partial derivative of L with respect to x, y, and lambda and set them all equal to 0. So we write partial L over partial x equals 0, and so on. This gives us three equations with three variables x, y, and lambda, which are then eliminate and substitute. Next, take the second order derivative f double x equals partial squared f over partial x squared, f double y equals partial squared f over partial y squared, and fxy equals partial squared f over partial x partial y. Next, the Hessian determinant. Since there is a constraint, we use a special formula. H equals gx squared times f double y minus gy squared times f double x minus 2 times gx times gy times fyx. And then the example problem, let's solve this example. 10x plus 12y minus x squared minus 2y squared subject to x plus y equals 10. We form the Lagrangian. L equals 10x plus 12y minus x squared minus 2y squared plus lambda times 10 minus x minus y. Now take the partial derivative. Partial L over partial x equals 10 minus 2x minus lambda equals 0, and so on. Next, solve the system of equation. From equation 1 and 2, we can express lambda. Lambda equals 10 minus 2x equals 12 minus 4y. Solve this to find x and y. We also use the constraint x plus y equals 10. From solving, we get y equals 11 over 3, x is 19 over 3, and lambda is negative 8 over 3. So the stationary point is 19 over 3 and 11 over 3. Now check the second order condition. The f double x is minus 2, the f double y is minus 4, and fxy is 0. Then the Hessian determinant is h equals minus 2 times minus 4 equals times minus 0 squared equals 8. Since h is greater than 0 and f double x is negative, this means we have a relative maximum. Therefore, the function reached a local maximum at the point x equals 19 over 3 and y equals 11 over 3, subject to the constraint x plus y equals 10. Now let's look at the optimization without constraint. This used when we want to maximize or minimize a function without any restriction or condition. In economics, consumer satisfaction is represented by a utility function usually written as U. The utility function depends on two goods, X and Y. To analyze how utility change, we take the partial derivative. Partial U over partial X means the partial derivative of U with respect to good X, and partial U over partial Y means the partial derivative of U with respect to good Y. Here's an example. Let's maximize the utility function. U equals 24x plus 32y minus x squared minus y squared. Step 1, we find the marginal utilities or partial derivative. Partial u over partial x equals 24 minus 2x, and partial u over partial y equals 32 minus 2y. The second step is find the maximum utility. Set the first order derivative to 0, and then we got the x is 12 and y is 19. So the stationary point is 12 and 19. The third step is second order condition. The f double x is minus 2, and f double y is minus 2, and f xy is 0. And then the Hessian determinant h equals minus 2 times minus 2 times minus 0, minus 0 squared equals 4. Since the determinant is greater than 0 and the f double x is negative, this confirms a local maximum. And then last, the result of maximum utility, we substitute the x equals 12 and y equals 16 into the original function. The original function is u equals 24x plus 32y minus x squared minus y squared. And then after we substitute, we got the u equals 24 times 12 plus 32 times 16 minus 12 squared minus 16 squared, and then the result is 400. So the maximum utility is 400 when the consumer consumes 12 units of good X and 16 units of goods Y. That's all from me. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akilla Riznaini and I'm from class MB-48-01. Today, I'm going to explain one of the most essential tools in economics mathematics, matrices. So, a metric is a rectangular arrangement of numbers organized in rows and columns and placed inside square brackets. Matrices help us organize data, perform mathematical operation efficiently, and solve complex system of equation, especially in business and economics. Throughout these sessions, we will learn about the type of matrices, how to do matrix operations, and how to apply matrices to solve linear equations using methods like inverse matrices and Cramer's rules. So let's start with the basic concepts. A metric is a rectangular arrangement of numbers written inside square brackets and organized in rows and columns. Here is a matrix. Metric A is a 2 by 2 identity matrix. You can see that it has 1 on the diagonal and 0 elsewhere. Metric B is a 3 by 3 diagonal matrix because only the diagonal has non-zero values. Matrix C is a row matrix with just 1 row, and metric D is a column matrix with only 1 column. Okay. Wait. Now let's move on to matrix number operation. We'll start with addition, scalar multiplication, and matrix multiplication. Each operation has its own rules. First is matrix addition. We can only add matrices that have the same dimension. Here, both A and B is 2 by 2. So we add elements by elements, 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. That give us the resulting matrix 6, 8, 10, and 12. Scalar multiplication means we multiply each element by the scalar, in this case is 2. 1 times 2 is 2, 2 times 2 is 4, and so on. The result is another matrix of the same size. The last one is matrix multiplications. Now let's multiply two matrices. For this, we need the number of columns in the first matrix to equal the numbers of rows in the second. Matrix A is one row and two columns. Matrix B is 2 rows and 1 column. So we can multiply them. Multiply the row of A by the column of B. 1 times 3 plus 2 times 4, that's 3 plus 8, which equals 11. So the result is a 1 times 1 matrix or a scalar. Okay, let's move to here. Okay, now we move on to the determinant, a special value that we can calculate from square matrices. The determinant helps us know whether a matrix is invertible. If the determinant is 0, that matrix has no inverse. So this is a 2 by 2 matrix. The formula for the determinant is top left times bottom right minus top right times bottom left. So 4 times 3 is 12 minus 2 give us 10. The determinant is 10, so matrix A is invertible. For a 3 by 3 matrix, we use the Serres method, a trick that helps us multiply diagonals easily. So step 1, write down the matrix, then copy the first 2 columns next to it, and then multiply the diagonals from top left to bottom right and sum them, and then subtract the sum of diagonals going bottom left to top right. In this example, we use the Serres method here, of course. So first, we multiply the diagonals from left to right. 1 times 4 times 6 is 24. 2 times 5 times 1 is 10. And 3 times 0 times 1 is 0. Now we subtract the diagonals from right to left. 3 times 4 times 1 is 12. 2 times 0 times 1 is 0. 1 times 5 times 1 is 5. The final determinant is 34 minus 17, which is 17. Okay, let's continue here to adjoint matrix. Now that we have learned how to find the determinants, let's move on to the adjoint of a matrix. The adjoint is the transpose of the cofactor matrix. It's used when we want to find the inverse of a square matrix. This is a 2 by 2 matrix, so we have to find the cofactors of each element. Minor of 1, position A11 is 4. Minor of 2, position A12 is 3. So the cofactor is minus 3. Minor of 3, A21 is 2. The cofactor is minus 2. Minor of 4, A22 is 1. So the cofactor matrix is 4, negative 2, and 1. 4, negative 3, negative 2, and 1. Now we make the transpose of that matrix, which means switching rows with columns. So the adjoint of a matrix A is 4, minus 2, minus 3, and 1. So remember, cofactor, then transpose equals adjoint. Okay, let's move on to inverse matrix. Next, we will learn how to find the inverse of a matrix. The inverse of matrix A is written as A inverse. It only exists in the determinant of A is not equals to 0. The formula is A inverse equals 1 over the determinant of A times the adjoints of A. Now I will show how to find the inverse of a 2 by 2 matrix using the adjoint method. The formula is A inverse equals 1 over the determinant of A times the adjoint of A. Step 1. We multiply the top left by the bottom right. 1 times 4 equals 4, then subtract the product of the top right and bottom left. 2 times 3 equals 6, 4 minus 6 equals -2. And then we calculate the minor of each element by covering its row and columns and then applying the sign patterns. Plus, minus, minus, plus. So the cofactor matrix is 4, -3, -2, and 1. We now transpose the cofactor matrix by switching the rows and columns. The first row becomes the first columns and the second row becomes the second column. That gives us the adjoint matrix 4, -2, -3, and 1. Now we multiply every element in the adjoint by over -2. 4 divided by -2 is -2. -3 divided by -2 is positive 1.5. 1 divided by -2 is -0.5. So that was the final result. We will continuing to solving linear equation with matrix. Now let's apply that we have learned to solve a system of linear equation using matrices. So we'll use this form where A is the coefficient matrix, X is the variable matrix, and C is the constant matrix. Here is the example question. 2x plus y equals 5 and x plus 3y equals 7. The first step, 2 times 3 and then minus 1 times 1 equals 5. So the determinant is 5. And then from previous step, we've already found the adjoint matrix. The top row is 3 and -1, and the bottom row is -1 and 2. So we just now have to multiply each element by 1/5. 3 divided by 5 is 0.6, -1 divided by 5 is -0.2, and so on. So the inverse of A is 0.6, -0.2, -0.2, and 0.4. Now multiply the inverse matrix with the constant matrix C. The top row is 0.6 times 5 is 3, -0.2 times 7 is -1.4, 3 minus 1.4 equals 1.6. The bottom row, -0.2 times 5 is -1, 0.4 times 7 is 2.8, -1 plus 2.8 equals 1.8. So the solution or the final result is x equals 1.6 and y equals 1.8. And then we've already came to the last part, which is the Cramer's rules. So, Cramer's rules give us another way to solve a system of linear equation using determinants. We replace one column at a time in matrix A with the constant matrix C and define its determinant by the determinant of A. Now, I will solve this system using Cramer's rules. We will calculate the determinant of matrix A's and then replace each column with the constant matrix to find X and Y. Matrix A is the coefficient matrix, so the constant matrix C contains the numbers on the right-hand side, 8 and 20. And then 1 times 4 minus 2 times 3 equals 4 minus 6, which is -2. Now we replace the first column of A with the constant. So matrix A1 becomes A, 2, 20. And 4. The determinant is 8 times 4 minus 2 times 20. That's 32 minus 40, which equals -8. Now we replace the second column with the constant. So matrix A2 becomes 1, 8, 3, 20. The determinant is 1 times 20 minus 8 times 3. That's 20 minus 24, which equals -4. Here. So to find X, we divide negative 8 by negative 2. That gives us x equals 4. So to find y, we divide negative 4 by negative 2. That gives us y equals 2. So the final result to the system is x equals 4 and y equals 2. I think that's all from me today. Thank you for listening, and I hope this helped make math choices a lot more useful. Bye!